Hey everyone, welcome to today's Explainer. Today we are unlocking the incredible secrets of the atom. We're going to systematically break down the science of provoked nuclear reactions, looking really closely at the fundamental physics that actually allow us to unleash some of the most concentrated forms of energy in the entire universe.
So I want you to think about this for just a second. What is the real, fundamental difference between the immense energy powering a massive nuclear submarine running deep underwater and the limitless energy powering the sun shining up in the sky? Well, the answer comes down to two very different, unbelievably powerful atomic dances.
All right, let's dive right into this. Here's exactly what we're covering today. First, the basics of fission, then chain reactions and the dark side of fission. After that, we'll switch gears to the power of fusion, the extreme conditions it requires, and finally, a good old fission versus fusion showdown.
Okay, Section 1. The basics of nuclear fission. Breaking the atom.
So, if you're taking notes, here's the formal definition straight from our source material. Nuclear fission is a stimulated reaction where a heavy nucleus is divided into two lighter nuclei under the impact of a neutron. The absolutely crucial word here is stimulated. This isn't something that just magically happens on its own out of nowhere. It's a provoked reaction. We actively have to trigger it by bombarding the atom.
To put that into perspective, imagine a game of pool. We take a slow thermal neutron, which only has a tiny kinetic energy of about 0.02 electron volts, and we fire it straight at a heavy, fissile uranium-235 nucleus. It's exactly like hitting a cue ball right into a tight rack of billiard balls. The uranium absorbs that neutron, becomes super unstable, and just instantly splinters apart into lighter elements like cesium and rubidium, or maybe xenon and strontium.
Moving right along to Section 2. Chain reactions and immense energy.
But here's a really important question for you. When we split that uranium atom, we don't just perfectly get two lighter nuclei. Think about the mathematical remainder of that fission equation. What actually happens to those extra neutrons that get kicked out when the heavy atom breaks apart?
Well, it sets off an absolute cascade. This is the famous chain reaction. When that very first uranium-235 nucleus splits, it lets out several loose neutrons. And those newly emitted neutrons, they don't just sit around, they become tiny new projectiles, flying outward and smashing into other nearby fissile uranium nuclei, forcing them to split too. It multiplies insanely fast, creating this exponential cascade of atomic division that can easily spiral totally out of control.
Now, all of that rapid-fire smashing releases an absolutely unbelievable amount of energy. But physically, where does that energy go? Our source tells us it shows up in a few very specific physical forms. Primarily, it becomes the physical kinetic energy of those fission fragments flying apart, the kinetic energy of the newly emitted neutrons zipping through space, and the highly penetrating electromagnetic energy of gamma rays. It is literally raw, phenomenal power.
Which brings us to Section 3. The dark side of fission.
Look, while we do successfully harness fission in modern nuclear power plants, our source explicitly outlines some severe consequences associated with it. First off, there are major health impacts. Exposure to this kind of radiation can lead to elevated cancer risks, especially leukemia and thyroid cancer. Plus, there's the looming persistent threat of massive radioactive contamination in our air and sea if something goes wrong. We've seen tragic historical examples of this, like the Chernobyl disaster in Ukraine back in 1986 and Fukushima in Japan in 2011. Both of these catastrophes caused widespread contamination and forced the sudden evacuation of thousands of people. So while fission is an incredibly powerful tool, it definitely leaves a dangerous legacy.
All right, let's pivot over to Section 4. The power of nuclear fusion.
So, let's get this definition straight too. Nuclear fusion is a stimulated nuclear reaction that consists in the binding of two light nuclei to form one heavier nucleus. Think of it as the exact opposite of fission. Instead of breaking a heavy atom apart, we are taking super lightweight atoms and forcefully jamming them together.
And what are the raw ingredients for this? Usually isotopes of hydrogen. We've got standard hydrogen, sure, but we also have slightly heavier versions like deuterium, which has one neutron, and tritium, which has two. These are the lightweight building blocks we use when we attempt to pull off a fusion reaction. So how does that look when it actually happens? Well, when you combine deuterium and tritium, they fuse together to form a brand new, heavier nucleus, helium, and they kick out a solitary neutron.
And this tiny, microscopic atomic merger releases a massive, massive burst of energy.
But of course, there's a catch. Section 5. The extreme conditions for fusion.
The big roadblock here comes down to basic physics, specifically Coulomb's law. We're trying to merge two positive nuclei together, right? But what do two positive charges naturally want to do? They totally repel each other. So we have this massive natural barrier standing in our way. We have to somehow overpower that strong repulsive force.
So how on earth do we force them together? We basically have to give these nuclei so much kinetic energy that they smash into each other before they even have the chance to push away. And doing that requires insane heat. To put this into perspective, to make fusion happen, we need temperatures around 10 to the 8th power Kelvin. That is 100 million Kelvin. That's almost 10 times hotter than the very center of our sun. So yeah, it takes a literally mind-boggling environment to trigger this reaction on Earth.
Which leads us to Section 6, Fission versus Fusion, the ultimate showdown. Let's weigh them against each other based on everything we've learned. The advantages of fusion are just incredible. For equal amounts of mass, fusion actually yields more energy than fission. On top of that, its fuel source, hydrogen, is incredibly abundant in nature and way cheaper to extract than hunting down rare uranium-235. Plus, fusion produces a tiny fraction of the radioactive waste. Honestly, it sounds like the perfect energy source, doesn't it? But fission still holds one monumental advantage. We actually know how to control it properly. Because we've mastered controlling the fission chain reaction, we can use it right now, today, for civilian purposes in our nuclear power stations.
And that leaves us with perhaps the greatest scientific puzzle of our time. If fusion gives us way more energy, runs on universally abundant fuel, and creates practically no dangerous waste, how close are we really to perfectly controlling a 100 million degree reaction right here on Earth? It's a huge, profound challenge that's waiting for the next generation of physicists, which, hey, might just be some of you watching today. So keep studying, keep questioning how the universe works, and I'll catch you in the next explainer.